Thank you very much. You almost pronounced it well. So I think you're all hungry now. So try to keep it in time, maybe a little bit faster. There's a bunch of names on this first slide, which are colleagues working on a program that I'm going to present, where it's a combination of people that have experience in structures like me, people involved in subsurface matters, and then most of those colleagues are actually here in the conference. And we have a couple of colleagues that are mainly focusing how to get the stakeholders involved in research programs. So I'm going to present a bit about our research program. I will touch on these different points of view that we have. Yeah, I don't have to tell this audience that we are facing a problem which has a large societal impact. Not the least because we have the newspapers filled, and we also have, I would say, an increasing attention because of damage which is occurring at places where there are multiple causes, multiple subsidence causes, but also multiple other causes than subsidence. And there's really a discussion about who's responsible and who's accountable for the damage. And we've seen a talk about Groningen. In Groningen, it's arranged. You can go somewhere, you can ring a button, and you can claim a file. But we now see that the discussions are all over the place. And this nice picture from my colleagues in Utrecht shows a couple of activities. I think most of those activities have been presented somehow in this conference. So you go from quite deep, like oil and gas extraction, to less deep, so to say, into shallow sources. And what we typically see in our country is that if you go anywhere in the Netherlands, most likely there are more drivers that relate to subsidence. And one of the issues is then how can we then, on the forefront, predict what the effects could be on buildings and infrastructure, on the built environment. We are tackling this issue by attempting or aiming to build what we call a chain of models, or model chain, where we go from left to right. So we want to identify for any subsurface activity how this causes subsidence, but how that subsidence then, through soil structure interaction, in the end leads to building damage. So we go from relatively large scales, step by step, to the building scale. We have a number of particular issues that we really would like to address in our work. And the first one is about this disentanglement of the subsidence drivers. So we have different subsidence drivers, but what is the contribution of each of them in the end to this damage? We want to get a hold on that. What's also relevant is that if you look into predictions of subsidence, particularly in this case for the Netherlands, they are typically on a certain grid, like 100 by 100 meters, which is far from the scales which are of interest if you want to look into buildings. So we have to look how we can go from those scales towards what we need to say something about buildings, to go to the building scale. Then, of course, the issue is when there's a building on top and you have subsidence, the building itself also has a lot of influence on the behavior of the soil directly underneath. So there's an interaction there. So we want to take a look into that one. And in the end, we work with the concept of fragility functions, which is well known in seismic engineering, well developed there. Because in the end, we want to say something risk-based, so probability-based. So then the concept of fragility function seems to be a rather straightforward way to apply. And I want to say some words about all those four topics. And of course also refer to other talks and posters in this conference. Because if you look into disentanglement of subsidence drivers, some studies are underway. One of the studies actually is going to be presented this afternoon by Manon Verberne. She's in the audience here. She's already getting a bit nervous for the talk, but you're all welcome to hear her. And she builds more or less also on what has been published before by colleagues of mine in this paper, which was published last year, where we actually, if you look into these figures, you see in this case 3 different human interventions, and 3 different subsidence contributions here illustrated. I'm not going into details, but if you go to the right, you can see that if you have 3 different subsidence effects, you can, in fact, add them up to come to the overall subsidence. What we typically see if you have observations, we only have this red line. So we want to know how to disentangle those contributions. So let's then say this about this. You can hear more this afternoon. The second part is about this downscaling, which is an interesting one, because if you do predictions on a regional scale on this larger grid, how can you then go to these smaller building scales? How can you do that? Well, in this case, for the Netherlands, we have the geological service of the Survey of the Netherlands in-house, and there also, besides the geological information, there's also information based on CPTs in-house. So it's strange. I'm pointing that direction. It's over there. And we use that information, which we have in-house, to predict more or less in a probabilistic way how the surface behavior on the smaller scales is. It's really work in progress, so I hope that in the next conferences more of that will be presented. You can also talk with Thibaut Candelaar, who has a poster on this topic at the room where the posters are. And then my field of play comes in. Then we want to look into what's happening with damage. And to start with that, I like to use these very, very simple representations, because what you typically see, if you have a subsiding region, what happens to houses? They are sinking, obviously, they are sinking. We all know that, because the surface moves and the building move with them. But some of them won't, because some of them might be on piles. I think we had some, I think Gilles showed some pictures of that. You can even have differences there. But if you look to individual buildings, that's what's happening. They can sink, they can sag, they can hog, they can be a little bit torn apart, very, very little, and of course they can tilt. Most likely when you have local effects, it's a combination of these things which are happening. And what we typically see is that sagging and hogging seem to be the most dominant parameters that cause damage. But these are 2D representations. And in 2D we know quite a lot, but one of the things that we really would like to study is that how does that work in 3D? So the upper picture is when we look into the building and we have a part of the surface lowered, and then what's happening to the building and how this leads to damage in the building. And then a second part is that we want to look, okay, suppose that, because this is an ideal situation, which will never occur, of course, because in all cases it will be different than just a straight line in the middle of the building. So we're also going to do sensitivity studies, what's happening if you go diagonal with respect to the difference in surface movement. So that's ongoing work. So we wanted to check whether the vulnerability of a building in this case and in that case and in similar cases will be the same or will be different. And of course, a third item not in the plots is that also we have to look into what the building weight and especially the distribution of the building weight over the building, how that works in the end for the damage indicators. And the fourth item is the development of fragility functions. Maybe a rather complicated figure, but if you go to the left, what we do to the bottom left is a representation that we say, okay, you have a certain movement of the subsurface, but certain movement of the subsurface is described in probabilistic terms because we don't know exactly, but we know a bit about the stochastics, the statistics behind it. And on the upper left side, it's basically the same for the properties of the building and the materials of the building. So we have to put that information inside models and create. And we do a lot of nonlinear calculations so that we actually calculate cracks inside buildings and propagation of cracks inside buildings. And then you can draw curves like this, where we have what we call an intensity measure for the foundation movement versus a measure for the damage. In this case, it's crack width, but we are still investigating whether that's an appropriate one, because there are more around, we know that. We're also working here with the people from the TU Delft. We have a PhD student just started in this field, so that would be one of the topics that she will dive into. And here we have fragility functions, as we know them also in seismic engineering, where we have an intensity measure versus, in this case, the probability of damage related, in this case, to a width of a crack. So if we have that, and if we have that for not only a single model, but if we have that for a variety of models, and the variety of models, we link that to definitions, which is on the upper line, definition of building topologies, then we can have probability distributions per building topology of damage, and then we can link that to the surface movement predictions, and hopefully in the end come with reliable predictions of the damage. I have to go to the next slide. So, and one important point, of course, is that because since we are using models, and you can go anywhere with models if you start to vary, we also like to validate or calibrate our models with a lot of data. Some techniques are listed here. It's not exhaustive. We are still working on to see if we can actually monitor one or two sites where we can check whether our models actually work. There's again a poster of that presented by Zai, also somewhere in the room. So we look into both INSAR data. Lots of observations have been presented here, but also look into groundwater data as well as actually damage metrics on buildings. Some word about the applications.
Sorry, 3 minutes.
Yeah, it's I have 2 slides left. So about the applications, we think that first of all, this could be really of help when we want to make plans for new subsurface activities. So not only deep, but also undeep or shallow. We have a lot of plans for geothermal activities, for instance, in the Netherlands, and those questions are already on the table. So we think that really, if we can predict those risks well, that really would help in taking these well-informed decisions. The second part is when we have damage already occurring. There's a lot of debate whether that occurs due to reason A, B, or C, and apparently if there's one governmental party, the most of the attention goes to the government. But it's also really good to know what the contribution to the actual damage could be based on other drivers. So that would be a second application. And the third one is a nice debate which is going on in the Netherlands about spatial planning. We have like ambitions until 2030 to build almost 1 million new houses in the Netherlands. And apart from all kind of processes that hinder that tempo, we also need to check whether the regions that are vulnerable for subsidence, whether they are fitted for purpose if you look into this effect. So not only related to flood risk, but also if you want to look into the infrastructure, the local infrastructure, and to what it does with houses, etc., should be addressed there. As I said, we involve stakeholders in this program. We have stakeholder meetings. This was a picture of a meeting that we had last October, and where we also address the governmental parties. We have included consultants, but also partners that are actually working with all kind of data that might be of interest. Keep it short now. And yeah, some concluding remarks. As I said, we like to go towards a risk model. So we think there's really a need for that. It's all in probabilistic terms, so it cannot be in the end that specifically for your own house you know exactly where the damage comes from, but it's helpful. It's a helpful tool to say, okay, we have a certain probability that this damage will occur due to this driver. We want to implement it in a model chain, but we have identified quite some challenges. We are going to work on it, and we are studying this. And for us, it's we have like an end term in 3 years from now, but we are quite sure that at that time we are not finished at all. So that concludes my presentation.
Thank you. Thank you for the interesting presentation to move through the economical impact of this problem. Any question? Okay.
Thank you for this very nice presentation. I have one question about the damage modeling. How do you do that damage modeling?
You mean in the models that I showed? We are now using a lot of FEM modeling, so we do nonlinear calculations, so that we estimate where damage will occur due to a certain distribution of the subsurface movement. And when it occurs, we also want to look into how the crack propagates to the building. Is that what you?
What kind of mathematical model or numerical model do you use?
I cannot answer that because you know we're using those finite element models. I think Diana is the, I don't know if you know that, the Diana model is the Diana FEM model is the one that we are actually implying here.
Okay, thank you.
Yeah.
Hi, Chris. Thank
Hi,
you for the presentation. Just one question on what you define damage, because my impression is that, at least in the Netherlands, we don't see many collapse due to subsidence. So, yeah, if you are considering using other sources of damage to the house, other types of damage, and if so, if you have considered, apart from fragility curves, to use comfortability curves, which is the reduce of comfort of the people living in the building.
Yeah, first of all, your question about what do you regard as damage? Basically, it's the occurrence of cracks first, but then you have to define in the criterion, okay, numerically, you know, you can have a crack, but that doesn't mean that somebody actually observes a crack. So we are looking whether 0.1 millimeter or 0.5 millimeter, something like that in that region, you know, the discussions, is an appropriate measure to say, okay, whether numerically a crack occurs, well, that may be too, how you say that, too conservative to actually say now we have damage, because if nobody observes the damage and there's no really structural problem there, so why is it a problem? So as soon as it becomes visible, it can become an issue. And there's also, you can also talk about, okay, the first visible damage more or less you can regard as being an aesthetical problem. And then at a certain level, if it increases, you go to more functional demands, whether there's moisture ingress, etc., etc. So you want to avoid that. We didn't consider the other option yet, but that could be something to take a look at. Yeah.
Thank you.
Thank you for this interesting presentation. I have just one question regarding some of those meetings that you mentioned that, okay, stakeholders are involved and all these things. And then this special plan to build 1 million houses in Netherlands till 2030. I just wonder if there is also initiative from the civil engineering community in your network that they come up with some new plans for constructions, not to avoid subsidence area, rather to adapt to subsidence area by some new technologies in construction.
There are some initiatives on how you say that. I think first of all on local infrastructure we see quite some initiatives where the instead of having sand underneath the road, we have these lightweight materials like EPS type of things. So I think there's quite some initiatives, some pilot projects that have been built past years and still in progress. So at least on that level, I see that. We see on a building level, I don't see that. Yeah, there's some initiatives, but I don't see them being implemented yet. We have quite a thing related to wooden pile foundations, but that's indirectly related to subsidence. It's much more due to the lower water levels, and then the timber starts to actually rot. And there are companies that have developed some innovations that are really being implemented now in practice. Yeah.
Yeah.
Hi, thank you so much for the nice presentation. This is something which I also work with, so we can definitely discuss more. But I have a question regarding the stiffness of the building, and have you considered calibrating it to get the proper elastic and probably elastoplastic kind of behavior?
If you consider it, yeah, we should consider. That's what I said.
Okay,
Because
yeah.
now we have just started by building up a model based on material properties that are well known, because there are a lot of studies being done about the properties of typically Dutch houses. So we use those properties now in these models. But you're right. We should be. One of the things that we really should do, that's also the validation and calibration part, to see if we can have the actual behavior of this building measured in such a way that we can put it in the models. That's one of the challenges that we have, for sure.
Okay, thank you.
Thank you very much for your nice presentation. Of course,